Hi and welcome all. Today we'll see what are the applications of artificial intelligence and machine learning in structural engineering, including load prediction, structural design, material design, structural safety, retrofitting, and sustainability driven design. So it starts from load prediction till the structural safety. So how the application of AI and machine learning is used from design optimization to structural safety will be explored. Modern structures such as high-rise buildings, long-span bridges, offshore platforms, and smart infrastructure systems are becoming increasingly complex, and these structures are subjected to various loads, environmental conditions, and operational uncertainties throughout their lifespan. As the amount of structural data generated from sensors, simulations, inspections continues to grow, traditional analysis method may become time-consuming, and hence there is a need for intelligent decision-making tools that can process large volume of data and support engineers in design, analysis, monitoring, and maintenance activities. So in this case, artificial intelligence and machine learning provide techniques to learn pattern from data, make predictions, optimize design, and assist in engineering decision making. So these technologies are transforming structural engineering by enabling safer, more efficient, and more sustainable infrastructure systems. Next, we'll see how AI is used in various aspects of structural engineering application. Structural engineering problems are often complex and involves nonlinear behavior. Multiple design constraints has to be taken care during the design process, and there are different multi-objective problems to be solved, and it should also satisfy safety, cost, and sustainability criteria. AI techniques can analyze these complex relationships more efficiently. AI models can learn from past data, and it can learn pattern from historical data, experimental results, and numerical simulations. Once trained, predictions can be done for new situations without repetitive excessive calculation or experiments. It also reduces time, cost. Many engineering tasks require significant computational effort and manual work. AI can automate repetitive processes, reduce analysis time, lower the project cost, and minimize errors. It also helps in making decisions under uncertainty condition. Engineers often deal with uncertainties such as variable loads, material properties, environmental condition, and structural deterioration. AI helps analyze these uncertainties and supports informed decision making. So because of these advantages, AI is increasingly being used in structural engineering for prediction, optimization, monitoring, design, and maintenance application. So next is about what are the different techniques which are used for applications in structural engineering is being listed out. First is machine learning. So machine learning is a branch of AI that enables computer to learn pattern from data and make predictions. In structural engineering, it is widely used for strength prediction, damage reduction, and structural health monitoring. So next is artificial neural network. Artificial neural networks are computational models inspired by the human brain, and they learn complex relationship between input and output and are commonly used for predicting structural behavior, load carrying capacity, and material properties. Deep learning. So deep learning is an advanced form of neural network that uses multiple hidden layers. So it is particularly effective for analyzing large data sets, images, and sensor data. So the deep learning application include crack detection and vibration based damage monitoring of structures. Next is genetic algorithm. So genetic algorithms are optimization technique inspired by natural evolution. So engineers can identify optimal structural design by applying genetic algorithm, and multiple design alternatives are being searched through genetic algorithm while satisfying all the criteria like safety and performance requirements. And last one is reinforcement learning. And this is technique where an agent learns through trial and error method by receiving rewards or penalties. In structural engineering, it can be used for maintenance planning, adaptive control, and decision making under different changing conditions. So each of these AI techniques has unique application, and the choice of technique depends upon the engineering problem which is required to be solved. In the following slide, several applications of these techniques in structural engineering will be explored. First, we'll see how AI is used in prediction of load. Structural loads acting on structure are often dynamic and change with time. So these loads include traffic load acting on bridges, wind loads on high-rise structures, earthquake load acting on structures, and temperature effects. So these loads vary with respect to time, and AI models can learn load patterns from historical records and real-time sensor data collected from structures. By analyzing these data, the models identify trends and relationship in load variation. Once trained, AI can forecast future loads under different operating conditions, and this helps engineers better understand how a structure may perform in the future. For example, AI can be used to predict wind loads on tall buildings by learning from past weather data and structural response measurements. So these predictions can be used as input for structural analysis and performance-based design, ultimately improving the safety, reliability, and resilience of structures. Next, we'll see what are the steps involved in prediction of load using AI or machine learning model. The workflow shown here illustrates how AI can be used for wind load prediction. So first step, we need to collect historical wind speed data, weather parameters, and building characteristics. Weather parameters including temperature, pressure, humidity, etc. has to be collected to predict the wind load. And building characteristics involving height, shape, and location of the building has to be collected. Once the data are collected, these are given as input. And these inputs influence the wind load acting on a structure. In the second step, the collected data is provided to an AI or machine learning model. So machine learning models such as artificial neural network, random forest, or XGBoost can be used for training the data and predicting the wind load. The model learns the relationship between input variables and the corresponding wind loads. Once trained, the model predicts future wind load that acts on the structure. These predicted loads can be used in the structural analysis and design to evaluate safety and performance of structure. Next, we'll see how AI can be used in different aspects of structural design. AI can help engineers to select the most suitable material properties and proportion for a structure. For example, it can optimize concrete mix design or reinforcement requirement to achieve the desired performance while minimizing the material usage. The shape and dimensions of structural components involving beams, columns, trusses, and bridges can be optimized with the help of AI, and the objective is to achieve maximum structural efficiency while satisfying strength and serviceability requirements. We can also have multiple design alternatives, allowing to identify the most effective solution for the given problem if you are using AI model for optimizing the section. AI can also simultaneously consider factors such as material cost, construction cost, carbon emission, and resource consumption, and it also helps in developing design that are both economical and environmentally sustainable. So overall, structural design can be done by exploring large number of possibilities and identifying solutions that balance safety, performance, cost, and sustainability. For example, during the design of a RC beam, the beam optimization involving dimension and reinforcement detail can be achieved with the help of AI technique to carry the required load carrying capacity while reducing the material consumption and overall cost. One of the important applications of artificial intelligence in structural design is optimization. The objective is to obtain a design that satisfies safety requirements while minimizing material consumption, cost, and environmental impact. AI can optimize both material and geometry for efficiency. So material properties and structural geometry are optimized. Instead of relying solely on trial and error approaches, AI algorithms can automatically search for the best combination of beam dimension, member sizes, and material usage to achieve efficient structural performance. Multiple design alternatives is made possible by satisfying the cost, safety, and sustainability criteria. Each alternative can be assessed based on different objectives such as cost, safety, weight, and sustainability. Genetic algorithm is used for truss or beam optimization. So this figure illustrates the use of genetic algorithm for structural optimization. Genetic algorithms are inspired by the process of natural evolution. They begin with several possible design solutions and gradually improve them over multiple iterations. So as we can see that the truss optimization or beam optimization can be done with the genetic algorithm. And here the figure given here shows the structural optimization of transmission towers, which is done using genetic algorithm. And as we can see that on the left we are having initial configuration, tower configuration, which is considered as a parent, and genetic algorithm is being applied with a variable length and variable configuration. Genetic algorithm generates multiple design alternatives by modifying member arrangements and structural dimension. Each alternative is evaluated based on performance criteria such as strength, stability, and material usage. After processing, we are able to get the optimal configuration as a final output. So traditional designs are often conservative and may contain excess material. So AI-based optimization helps reduce over-design and material waste while maintaining the required safety margins. So as we can see that AI-driven structural design optimization enables engineers to develop safer, lighter, more economical and more sustainable structures by automatically exploring different possibilities of design alternatives. So next we'll see about prediction approach. So the previous one is optimization approach, where it is mainly used for optimization of dimension of trusses or beams. And next approach is prediction approach. To train an AI model for structural design, we need to have a large data set, and this data set can be generated by creating beam models with different span length, section dimension, material strength and loading condition. For each beam configuration, the design calculations are performed to determine the required area of reinforcement. Next, the input parameters are varied repeatedly to generate large number of valid design cases, and these valid design from the data set are used as data set for training the AI model. The AI model that learns the relationship between the beam parameters and the required reinforcement area. Once trained, the model can quickly predict the required area of reinforcement for the new beam configuration. So this is a way how the prediction approach can be used for structural design, and this is shown as an example of how the trained AI model can be used to predict the area of reinforcement. So previously we have seen the application of AI for structural design and optimization, and the present slide shows how AI can predict the reinforcement area for the given beam so that it can be used for both optimization approach as well as for the prediction approach. For example, if you want to design a beam, consider a beam which is having a span of 6 meter and a width of 300 mm and effective depth of 500 mm. Take it as an example, and concrete strength is of 30 megapascal. So instead of manually performing the design calculation, the trained AI model can directly estimate what is the reinforcement required for the given beam dimension, and to carry the given load, what is the required reinforcement area can be determined based on patterns learned from thousands of previous design data, which is given as a input. So this is how the AI can design. Next is about seismic analysis and design. So it is used to predict structural response during earthquakes. So during earthquakes, structure experience complex nonlinear behavior. An AI model can learn this behavior from simulation results or experimental results and quickly predict important response parameters such as interstory drift or displacement and damage level which has been occurred due to earthquake. Fragility curves represent the probability of structure reaching different damage condition under varying earthquake intensities. So the machine learning can develop these curves directly from large data sets. Bridge analysis and monitoring. In the case of bridges are subjected to repeated traffic loads, wind loads and environmental effects throughout their service life. So AI model can analyze material degradation trends and stress cycles which are being observed in the bridges due to the application of different types of load and environmental condition to estimate the remaining fatigue life and load carrying capacity of bridge components. So it can also process continuous sensor data collected from bridges. By monitoring changes in structural behavior, AI can identify abnormal performance and provide early warning before significant damage occurs. So early detection of performance deterioration is made possible, and this enables proactive maintenance and improves safety of the structure and extends the service life of bridge structure. So next we'll see how the design optimization for bridge can be done with the help of AI. So as we have seen two approaches for structural design, one is optimization approach and another one is prediction approach. So based on optimization approach, the cross-section optimization or member configuration optimization, truss configuration optimization can be done. So similar way here, it can also be used for the optimization of bridge design during the design stage. Optimization algorithm evaluates numerous design alternatives to identify the most efficient configuration. Parameters such as girder depth, member dimension, and cable arrangement can be optimized while satisfying strength and serviceability requirements. One commonly used technique in the case of bridge design optimization is particle swarm optimization or PSO. It is inspired by the collective behavior of birds and fish. The algorithm searches for the best design solution by continuously improving solution based on previous experience. As a result, we will be able to get the more economical and more sustainable bridge design by reducing the material usage and construction cost. So this is how the AI can be used for optimization of bridge design. AI can also be used for material design optimization. It is used for high performance concrete mix optimization where the best combination of concrete ingredients to achieve required strength and performance is being obtained. Machine learning models can estimate concrete compressive strength and durability from concrete mix proportions without extensive laboratory testing. It also supports the development of sustainable concrete by incorporating recycled aggregate and supplementary cementitious material while maintaining structural performance, and it helps in developing the green construction materials where we are able to evaluate multiple material combination and we are able to support sustainable construction practices. So therefore, AI enables faster and more sustainable material design, and optimization is being done if with the help of AI model. Next is about retrofitting and rehabilitation. So we are in the case of retrofitting and rehabilitation, it is very much important to know where the rehabilitation has to be done or retrofitting technique has to be used. So in case of old structures, we will not be able to have sufficient data. So digital records may not be available for old structures or heritage structures. So AI trained on structural health monitoring plus visual inspection can suggest retrofit strategies. So sensor data which is being collected recently and image-based assessments which are being collected based on the images of the building, the structural condition and deterioration trends of the building will be obtained. And this deterioration trend and structural condition of the building will be used for training the model where the engineers will be able to formulate the retrofit or strengthening strategies required to extend the service life of aging structure efficiently. For example, AI can predict where the retrofitting or rehabilitation technique has to be used or where the carbon fiber reinforcement has to be done in the existing structural element to strengthen the structure. So this connects design with life cycle safety. It also leads to sustainable driven solution design. AI for sustainability driven solution focuses on reducing the environmental impact of structures while maintaining safety and performance. By analyzing thousands of design alternatives, it can identify structural configuration that use lesser material and produce lesser embodied carbon. It also helps engineers to select low carbon concrete mixes and recycle materials and optimize member sizes during the design stage, leading to more sustainable and resource efficient construction. Construction stage design is also a critical aspect of structural safety because A structure may experience different loading and support condition during construction than the final stage or in service stage. So AI can simulate various construction sequences and identify potential stability issues which are faced related to temporary support, scaffolding and stage erection. By predicting the risk before construction begins, AI helps engineers develop safer construction plan. So by integrating AI with Building Information Modeling BIM enables the real-time monitoring condition of the structure, and it can also monitor and optimize the construction activities in real time, reducing delays and improving efficiency and enhancing the overall site safety of the structure by reducing the on-site accidents, construction risk and delays. So finally, AI analyzes stress, strain and vibration data to detect abnormal patterns indicating potential crack initiation or fatigue zones. Yearly identification is made possible with the help of AI and structural health monitoring data, and it allows for preventive maintenance, reducing downtime and avoiding catastrophic structural failure. So a structural health monitoring system collects continuous data while AI interprets it in real time to assess performance and detect deterioration in structure. So this live feedback loop enables predictive maintenance and supports decision making for repair or load adjustment. So AI bridges the gap between design and operation by continuously validating structural performance against design assumption. Lifecycle monitoring data help refine future designs, promoting adaptive and performance-based resilience in structural design. So as a key takeaway, in conclusion, we can tell that AI is revolutionizing structural engineering by improving design efficiency, resource utilization, and structural safety. Its continued adoption will contribute to the development of smarter, safer, and more sustainable infrastructure systems for the future. Thank you all.